Organic Chemistry, Chem 213, Exam 4 Material, Part 1. Chapter 20, Carboxylic Acids and Nitriles. The importance of carboxylic acids. Note that your textbook likes to write COOH as CO subscript 2H. Carboxylic acids and their derivatives are carbonyl compounds in which the acyl group is bonded to, and this is the group we're talking about right here, is bonded to an electronegative atom such as oxygen, halogen, nitrogen, or sulfur. This is in contrast to aldehydes and ketones. Aldehydes and ketones would not have an oxygen here. They would have either a carbon group or a hydrogen, depending on if it was an aldehyde or ketone. So what this does is when you have an electronegative group here, it can act as a leaving group in substitution reactions. Carboxylic acids are also starting materials for acyl derivatives such as esters, amides, and acid chlorides. And also carboxylic acids are abundant in nature from oxidation of aldehydes and alcohol in metabolism. Naming carboxylic acids. Carboxylic acids are on the top of the list of priority, so they're always going to be the parent, and the numbering system is going to be based on the carboxylic acid. If we're deriving a name from an open chain alkane, replace the terminal E of the alkane name with oic acid. The carboxyl carbon is always carbon number 1. So in my example here of propanoic acid, this carbon that is part of the carbonyl group is always carbon number 1. So let's take a look at a couple of our examples here. We have a total of 3 carbons, 1, 2, 3. Propanoic acid, the E was removed. Oic is placed there, and there is a space between the oic name and acid. There is a space there. If you have a substituent coming off of your main chain, so here we have our main chain here with the carboxylic acid group. The carbonyl carbon's carbon number 1. So relative to that, I have a substituent of methyl coming off carbon number 4. 4-methyl pentanoic acid. We can also have a situation where you have more than one carboxylic acid. Let's look at this third example. In the name, we can see down here we have dioic acid. With organic chemistry, they always put the multiplier exactly in front of what there's more than one of. The di is in front of the oic acid. That tells us there's 2 carboxylic acid pieces in here. Notice that on the parent chain, octane, the E is retained, just as we've done before when we've had a multiplier following it. Here's our parent chain. We have a carbonyl group at carbon number 1 going from left to right, also on carbon number 1 going from right to left. So let's see what breaks the tie. As we go in from left to right, notice that on carbon number 3, I have an ethyl group. If I go from the other direction, coming off carbon number 1, 2, 3, I have a methyl group. So this is a situation where we have a tie going from right to left or left to right based on priority. Remember, the carboxylic acids are going to be 1 and 8 no matter what. How we break a tie when they're of equal priority is through alphabetizing. E comes before M. So the direction that we're going to be using to number this carboxylic acid is from left to right. Because remember, once we choose a direction, you have to maintain the direction for the rest of the molecule. 3-ethyl 6-methyl octane dioic acid. Alternative names. Compounds with the carboxylic acid piece bonded to a ring are named using the suffix carboxylic acid. The COOH carbon itself is not numbered in this system. It's the carbon that it's attached to that becomes carbon number 1. This is carbon number 1. So we look clockwise or counterclockwise to give the next substituent its lowest value. And we can see here on this one, if we were to go clockwise, bromo would get the number 3. The other direction, the number is larger. So this would be the direction for this one. This one would be clockwise. The name of this compound would be 3-bromo cyclohexane carboxylic acid. Note that again the E is retained in this style of naming. We can also have a carboxylic acid on a ring that also has a double bond. Let's look at an example of that. We know that carboxylic acid has top priority. The carbon that it's attached to on the ring becomes carbon number 1. We're going to do something similar as we did in the previous example. We're going to go in the direction that causes the multiple bond to have the lowest number, either clockwise or counterclockwise. In this case, going clockwise, the double bond starts on carbon number 1 and ends on carbon number 2. The 1 in the name here is telling the reader of the name where the double bond starts. 1-cyclopentene carboxylic acid. Common names for formic acid and acetic acid are common names that you are responsible to know, and you can also find these on table 20.1. Draw the structures for the following. Go ahead and pause the video and come back and check your work. So for some of these I did line structures, other I did condensed structural formulas. We have 2,3-dimethyl hexanoic acid. This would be carbon number 1 right here. 2, 3, 4, 5, 6. I do have 6 carbons. Coming off carbon number 2 and 3 are 2 methyl groups. 2-cyclohexene carboxylic acid. Cyclo, so that means I'm going to have a ring of 6, and my carboxylic acid is carbon number 1. This is carbon number 1, and when I draw the structure, I have the choice of either going clockwise or counterclockwise, and my double bond needs to start on carbon number 2. In this case, I've drawn it clockwise. Here's carbon number 2, and it ends on 3. Butane dioic acid. This die right here tells me I have 2 carboxylic acid pieces. 1, 2, 3, 4. There's only 4 carbons total, including the carboxylic acid carbons. Two amino propanoic acid. Its common name is alanine. In fact, it's one of our amino acids. The amino group is known as the NH2 group. 2-amino propanoic acid. I have 3 carbons, single bonded, and coming off carbon number 2 would be my amino group. We have carbon 1, here's carbon number 1, 2 and 3, and here is coming off carbon number 2, an amino group. Its IUPAC name is 2-amino propanoic acid. The name of the amino acid happens to be alanine. 2-hydroxypropanoic acid. Its common name is lactic acid. And yes, this is the same lactic acid that when you exercise and they tell you you're feeling the burn in your muscles, that's the lactic acid that's produced during that process. So let's look at its structure. Propanoic acid, that's the parent. That would be 3 carbons with a carboxylic acid, carbonyl carbon on carbon number 1, and coming off carbon number 2, I have a hydroxy. You use hydroxy when OH does not have priority. For this slide, I have 3 structures. I would like you to give the IUPAC name. Go ahead and pause the video and come back and check how you did. My carboxylic acid is right here, so this is carbon number 1, 2, 3, 4. In fact, I have my double bond starting on carbon number 4, a total of 6 carbons. 4 4-hexene, there's the E here for the double bond, 4-hexenoic acid. Remember, carboxylic acid is understood to be carbon number 1 when it's on a straight chain like this. We don't indicate a numbering system because it's understood it's number 1. And carboxylic acids are at the top of the food chain in order of priority for nomenclature. Here we have a CH3 group also coming off of this carbon. It's showing us 2, and you guys have seen me do this before, where I transform it to a branch. Sometimes it makes it easier to name. I have 1, 2, 3, 4 carbons in my parent chain, so its last name is going to be butanoic acid, and methyl is coming off carbon number 3, 3-methyl butanoic acid. For the last one here, here's my parent chain. This is carbon number 1. The carboxylic acid carbon is always number 1. And bromo is coming off of this carbon here. This is the one it's coming off of. If you want to rewrite it, you can do that. So we have carbon 1, 2, 3, 4. Bromo's coming off of 4 and 5 carbons total. So it would be a pentanoic acid with bromo coming off of 4. 4-bromo pentanoic acid. Structure and physical properties of carboxylic acids. The carboxyl carbon is sp2 hybridized, it's planar, and 120 degrees. Carboxylic acids form hydrogen bonds existing as cyclic dimers held together by 2 hydrogen bonds. This is a picture of acetic acid. In fact, it's acetic acid dimer. The hydrogen that is bonded to the oxygen here. Remember, oxygen is more electronegative, and whenever hydrogen is directly bonded to FO or N, hydrogen bonding can happen. This hydrogen is going to be hydrogen bonded. That's why this line is a dotted line and not a solid line. This hydrogen is hydrogen bonded to this oxygen. And what's going to happen is we get what's known as a dimer. Dimer being 2 pieces. Carboxylic acids form dimers. You may be responsible in this class to show me a dimer, not necessarily of acetic acid, but maybe other kinds of carboxylic acids. When you show me the dimer, this piece right here is going to be the same for all carboxylic acids. It would be this group right here that would change. It'd be whatever R group would make whatever carboxylic acid we're looking at. These strong hydrogen bonds in our dimer causes the boiling points to be much higher than corresponding alcohols. So we have learned earlier that when we have alcohols hydrogen bond to each other, which causes them to have a higher boiling point than alkanes of similar molecular weight. What this statement is telling us is the hydrogen bonding in the dimer is actually stronger than the hydrogen bonding in an alcohol. Dissociation of carboxylic acids. Carboxylic acids are proton donors towards weak and strong bases, producing metal carboxylate salts. It's this hydrogen right here, that's the acidic hydrogen in a carboxylic acid. What makes something an acid is its ability to give up a hydrogen. So this is the one that's going to go away. In this example, we have a strong base, sodium hydroxide, and what's going to happen is our hydrogen here is going to join the OH, forming water, and this is a carboxylic acid salt. Notice that my oxygen here has a negative charge, and ionically bonded to that would be my sodium plus. Because we have an ionic bond, that's why this is known as a salt. Ionic compounds are classified as salts. Carboxylic acids with more than 6 carbons are only slightly soluble in water, but their conjugate salts are water soluble. If we have a small R group, we can have some carboxylic acids water soluble, and we know that because we know acetic acid, the component in vinegar, is water soluble. As the R groups get bigger, in any organic compound, solubility always decreases. What we're finding out here is if we have a much larger R group, in this case 6 or more carbons, we can convert it to its carboxylic acid salt, and those larger molecules become water soluble. Acidity constant and pKa. Carboxylic acids transfer a proton to water to give a hydronium ion and carboxylate anions. But H3O plus is a much stronger acid. The acidity constant, Ka, is about 10 to the minus 5 for typical carboxylic acids. Converting that to pKa, if you look at the bottom here on the right, we have the formula that minus the log of the Ka equals pKa, and the reason why we do this conversion is so the numbers make a little more sense to us. So when we say the Ka is about 10 to the minus 5, it's actually easier for us to look at this and compare when we say the pKa is about 5. That's an easier number for us to compare. Carboxylic acids are also weaker acid than mineral acids, but stronger than alcohols. Weak acids just slightly dissociate. This is the dissociation reaction of a carboxylic acid in water. This is its corresponding equilibrium expression. Substituent effects on acidity. So the more things we have on our carboxylic acid, that can change its acidity. Table 20.4 shows us the acidity of some carboxylic acids. Here we have a carboxylic acid, total of 2 carbons, and instead of having any hydrogens there, it has a highly electronegative fluoro here, in fact 3 of them. What those fluoros are going to do is they're electron withdrawing, and they're going to cause all the electrons to be pulled towards it away from this hydrogen. Since the electron density is going to be pulled away from this acidic hydrogen, it's more able to leave. What makes something a stronger acid is it's easier to get out of there. So take a look at the different kind of substituents and what kind of effects they have. Now that we've had a chance to look at the table, let's take another look at electron withdrawing groups and electron donating groups. Electron withdrawing group. So this would be the example of those 3 fluoros on an adjacent carbon right here. An electron withdrawing group stabilizes the carboxylate anion. That means this O- would like to exist longer. When it's stable, that means it stays around longer. An electron withdrawing group attached to the alpha carbon, that would be the one right next to here, of a carboxylic acid inductively withdraws electron density. Anytime we use the word inductively, that means it's happening through the sigma bonds. So what's going to happen is through the sigma bond between this carbon and its alpha carbon, electron density is going to be pulled towards this. And what this does is it delocalizes the negative charge, thus stabilizing the carboxylate anion and then increasing acidity. An electron donating group destabilizes the carboxylate and decreases acidity. What it's going to do is it's going to be pushing electrons towards it, and that hydrogen's not going to want to get out of there. This is a nice graphic showing the example of the inductive effect, where there are, on the right-hand side here, stronger acids. So on my alpha carbon here, I have 3 chloros, and you can see that that's a much stronger acid than if I have 2 chloros, 1 chloro, or none. When I have an electron withdrawing group, in fact a whole bunch of them, it increases its acidity. Fluoroacetic, chloroacetic, bromoacetic, and iodoacetic acids are stronger acids than acetic acid, since more of the acid is in the dissociated form. Let's take a look at the substituent effects on substituted benzoic acids. Groups that are deactivating and electrophilic aromatic substitution reactions increase the acidity of substituted benzoic acids. The acidity of benzoic acids can be used to predict electrophilic reactivity, since measuring acidity is easier. Our example here is showing us the Y group in the para position, and we can see that a weaker acid would be OH. The acid would be stronger the more electron withdrawing it is, pulling it away, so this hydrogen has the ability to leave when we pull it away. And we can see of these substituents, the strongest acid would be NO2 in the para position on our benzoic acid. Preparation of carboxylic acids. Oxidation of a substitute alkyl benzene with potassium permanganate or sodium chromate gives a substituted benzoic acid. These reactions were also covered back in section 1610 if you'd like to have more details. Primary and secondary alkyl groups can be oxidized, but not tertiary. When we have this carbon here, when it has an available hydrogen, so it has to at least be primary or secondary, it has to have at least one hydrogen, in this case it has 3, it's able to undergo this oxidation, and this carbon is going to be converted to a carboxylic acid. This reaction also works best if you have a group like NO2 para to it. Another reaction that we have seen before to prepare carboxylic acids, back in section 7.8, the oxidative cleavage of an alkene with potassium permanganate gives a carboxylic acid if the alkene has at least one vinyl hydrogen. These two carbons I have in green are the vinyl carbons, so it has to have at least one vinyl hydrogen, so this one actually has 2. For the cleavage reaction, what's going to happen is it's going to cut between these two carbons, and we're going to get a carboxylic acid from the piece here on the left. And because my starting material here also had this, that maintains right here, and this piece becomes also a carboxylic acid. This one actually gets 2 carboxylic acids only because of the R group that I have here. In the example down here, I have a carboxylic acid, and I have my carbon-carbon double bond here. What products would you expect from this oxidative cleavage? Go ahead and pause the video and then come check your work. How'd you do? Carboxylic acids can be prepared from alcohols and aldehydes under oxidation. These are reactions that we saw earlier in the semester. This is a primary alcohol undergoing strong oxidation, and it forms a carboxylic acid. An aldehyde undergoing oxidation also forms a carboxylic acid. Hydrolysis of nitriles. Conversion of an alkyl halide to a nitrile with cyanide ion, followed by hydrolysis, produces a carboxylic acid with one more carbon. This is best with primary halides because the elimination reaction occurs with secondary or tertiary alkyl halides. Here's my primary alkyl halide, sodium cyanide under an SN2 condition. This cyanide carbon here is now attached to my R group. The cyanide substituted where my halogen was. The halogen was the leaving group. The CN is now replacing it in the substitution reaction in an SN2. After the cyanide has substituted where the halogen was, a protonation occurs with acid. The cyanide carbon is now going to become the carboxylic acid carbon with a minor secondary product of NH3. This is where the nitrogen went to. Carboxylic acids can be formed from Grignard reagents. Grignard reagents react with dry CO2 to yield a metal carboxylate. These are limited to alkyl halides that can form Grignard reagents. More details would be in Chapter 17, Section 6 in your textbook. This first half is showing the Grignard reagent being prepared. What we're looking at here is CO2, dry ice, ether, and the second step is where we have the acid coming in, the protonation of our product. Complete the following reaction, pause the video, and see how you did. The Grignard reagent that's formed, and this is the carboxylic acid product. So your book at this point goes into a preview of some of the reactions of carboxylic acids. Carboxylic acids transfer proton to a base to give anions, which are good nucleophiles in SN2 reactions. Like ketones, carboxylic acids undergo addition of nucleophiles to the carbonyl group. In addition, Carboxylic acids undergo other reactions characteristic of neither alcohols nor ketones. Here's a graphic showing a few of the reactions carboxylic acid can undergo. In fact, they're quite reactive, so we're going to be seeing a lot of reactions with them. Off to the left here, they're showing us an alpha substitution. Remember, the carbon next door to the carbonyl carbon is the alpha position. Deprotonation, hydrogen is being removed, making an ion for us. A reduction reaction where the carbonyl group is gone and we have more bonds to hydrogen than we had before. Nucleophilic acyl substitution, the OH is going to be substituted for something else. Reduction of carboxylic acids. They can be reduced to yield primary alcohols. Carboxylic acids can be reduced to primary alcohols with either lithium aluminum hydride or borohydride, but not by sodium borohydride. Lithium aluminum hydride is difficult and often requires heating in tetrahydrofuran solvent to go to completion. Carboxylic acid, lithium aluminum hydride, THF, heat, and the second part of this reaction is the protonation. Borohydride is a more selective reagent since the reaction occurs rapidly at room temperature. It still requires THF. THF is an ether. It gives the reagent something to float around and meet each other. And we still have as the second step the protonation. So we briefly mentioned nitriles a few slides ago. Nitriles are closely related to carboxylic acids in naming by adding nitrile as a suffix to the alkane name, and the nitrile carbon is carbon number 1. On this example here, including the carbon in our nitrile, we have 5 carbons. Notice the E is retained in the name pentane, and nitrile follows. There is no space. The parent name of this compound is pentane nitrile. It also has a substituent coming off of carbon number 4 of methyl. 4-methyl pentane nitrile, all one word. Complex nitriles are named as derivatives of the carboxylic acids. What you want to be able to do is know how to name carboxylic acids well before you tackle naming the nitriles. You'll see in these examples, they'll give you what carboxylic acid the name was derived from. 2 carbons total. This came from acetic acid, the common name acetic acid, and it's actually used more than the ethanoic acid. Acetic acid, the acete part stays, the ic acid is removed, O-nitrile is added. If this carbon was a carboxylic acid instead of a nitrile, it would be known as benzoic acid. Taking off the oic acid ending and adding O-nitrile, benzonitrile. This last example is a little more complicated. It also has the nitrile group on a ring. What we learn from this is when the nitrile is on a ring, the carbon itself is not carbon number 1. It's the carbon on the ring that it's attached. And that's because the basis for naming comes from carboxylic acids. And when we had a carboxylic acid on a ring, we went ahead and changed the name to carboxylic acid. If this CN group was actually a carboxylic acid group, its name would be 2,2-dimethyl cyclohexane carboxylic acid. To name it as a nitrile, we would remove the carboxylic acid portion of its name and add carbon nitrile. So when our nitrile is on a ring, so when we have cyanide on a ring, the suffix becomes carbonitrile. Chemistry of nitriles. Nitriles and carboxylic acids both have a carbon atom with 3 sigma bonds to an electronegative atom, and both contain a pi bond. Both of these are electrophiles. One way to prepare or to synthesize nitriles is through dehydration. The reaction of a primary amide with SOCl2 or POCl3 or any other dehydrating agent will cause the preparation or the synthesis of a nitrile. This is not limited by steric hindrance or side chains. Notice here, this is supposed to be a degree C, not infinity C, so please make sure your slide is correct. This is my starting material. This happens to be an amide. SO, Cl2 and benzene, and 80 degrees. The carbonyl carbon is now going to be triple bonded to the nitrogen that was in my amide. You also have some minor secondary products of SO2 and 2 moles of HCl. Here's a graphic of some of the reactions of nitriles. Nitriles can undergo a reduction and form an amine. Nitriles can also be reacted with water to form amides, and that amide can undergo a further reaction to form a carboxylic acid. Nitriles can also react with Grignard reagents to form ketones. Reactions of nitriles. Let's look at hydrolysis first, the conversion of a nitrile to a carboxylic acid. The conditions required would be either acidic or basic and water, and the carbon that is the carbon in my nitrile becomes the carbonyl carbon in my acid. Nitriles can also react with organometallic reagents. Here we have a Grignard reagent where the R group is going to be reacting with the carbon here. This R group is my nucleophile attacking the carbon here. A pair of the electrons is going to go to the nitrogen, and we have an imine anion. This is the imine group, and because it has a negative charge, it's an imine anion. Water will come in, the nitrogen will be expelled, the oxygen will now be the carboxylic acid group, and we form a ketone, minor secondary product of ammonia. A nitrile can undergo a reduction reaction and form an amine. Here we have the reduction of a nitrile with lithium aluminum hydride in ether. The second part of the reaction is water. The carbon of our nitrile gets 2 hydrogens. The nitrogen also gets 2 hydrogens. There's no longer a triple bond. There's only a single bond between carbon and nitrogen. The mechanism of how this works is the lithium aluminum hydride in ether will cause the carbon and nitrogen to form an amine ion. More of the reducing agent will cause the nitrogen to have a single bond but a -2 charge and form a dianion. Water comes in and it protonates the nitrogen, forming an amine. The mechanism is a nucleophilic addition of hydride ion to the polar cyanide bond and yields an amide anion. The carbon-nitrogen double bond undergoes a second nucleophilic addition of hydride to give a dianion, which is protonated by water. Spectroscopy of carboxylic acids and nitriles. The OH group has a characteristic and very broad absorption at about 2,500 to 3,300. The carbonyl carbon, we will see it absorbs sharply between 1710 and 1760. Free carboxyl groups also absorb in the same range. Commonly encountered dimetric carboxyl groups absorb in a broad band around 1710. Now, I don't have a picture of the spectroscopy of nitriles, but I do have information for you. Nitriles show an intense C triple bond N bond absorption near 2250 for saturated compounds and 2230 for aromatic and conjugated molecules. Carbon NMR. The carboxyl carbon gives a signal very, very far downfield, 165 to 185. Aromatic and alpha-beta unsaturated acids are near 165, and saturated aliphatic acids are near 185. The nitrile signal for carbon NMR will be about 115 to 130. Proton NMR. The acidic hydrogen in our carboxylic acid gives a signal, in fact it's a singlet, at 12. It's the only thing that's that far downfield. In fact, sometimes the spectrum that they'll show you, they won't even actually show you the 12. They'll put it on there somewhere or even indicate in the text that there happens to be a signal at 12. Here we have a carboxylic acid at the benzyl position. The H on my carboxylic acid is at 12. The two benzyl hydrogens are about 3.5, and the aromatic hydrogens just above 7.